Well, good evening, everybody. Nice to be here. Nice to see everybody in. We have another show. It's another week, obviously. And Monday, here we are joined by Crowxe. Crowxe, are you there? Do you want to come off mute and say hello to everybody?
Hello?
Hello. How are you?
Yeah, I'm fine. Hello, Randy, and hello, everyone. Thanks for having me on this show. I think you're having some background noise. Loud this time, or it's okay?
It's fine. It's not a problem. Is it some kind of tannoy or something that's going off there?
It's the prayer calling and the nearby mosque.
Oh, right. Okay.
So I'm in Egypt. My name is Khalid, or you can call me Khalid. I joined the flat Earth debate maybe like 2 years ago. I learned a lot of things since that time from both sides actually, and been motivated more by the flat Earth side, of course, because if there was no flat Earth, I wouldn't have learned or accomplished anything. My presentation today could be taken in two aspects. The first thing, it's some knowledge that could be useful, or at least it used to be useful before the time of GPS and modern navigation. And the second aspect is it's being globe proof. So I'm ready to share my screen now.
1 minute. So, how long is it likely this tannoy thing likely to go on for?
Maybe 1 minute.
Right. Okay.
Let me close the window.
Right.
Okay. Here.
Yeah, that's a little bit better. He's got a beautiful voice, but it's quite loud.
Yeah, exactly.
Okay, so I'm assuming that you are a glober and you're going to be doing a presentation about the sun. What's the hope at the end of this presentation? Is the hope that you can measure the distance to the sun? Is that what you're trying to do?
No, it's measuring the angles of the sun. In the heliocentric model, the Earth goes around the sun in elliptical orbit, and it spins 15 degrees per hour, roughly 15 degrees. And it has an axial tilt. So all these the angles and rates, upon them we can predict where would be the sun position in relation to a point on the Earth, and we can do that, or we can define that angle by vertical angle and horizontal angle, which is like elevation and azimuth.
Okay.
So. Yeah.
If you bear with me, I'll transition you across, give it 10 seconds, and the floor will be yours.
All right.
Enjoy.
Yes, thank you. The solar analemma, I'll go through this presentation in 6 points. One, what is an analemma in general? Two, how to produce an image of the solar analemma in particular. Three, the solar analemma chart and what is it for. Four, the factors that govern the solar analemma. 5, how the factors work to produce the unique shape of the solar analemma. And finally, just a quick glance on the math and trigonometry needed to plot the solar analemma. So first thing, this is my own definition. According to my understanding, the analemma, or any analemma, is time lapse of a celestial body along one cycle of its movement, or one Earth year, overlaying one frame every 24 hours. Like, for example, on the top left is the lunar analemma, and it's taken during a lunar month. Top right is Venus Analemma, and I'm not sure if it's taken along one Earth year or Venus year. And the two bottom pictures are the solar analemma that we know. One of them is vertical and looks nice, like the chart that we usually see, and the other one on the right is leaning, and that depends on when you start taking your images that you take every 24 hours. So how to produce an image of the solar analemma? First thing, where to aim. You aim south if you're on the northern hemisphere. And second, what time to aim is local solar noon. And when to start imaging, on the 7th, 15th of 1st, these 4 dates you date. Basically, if you, in any of these dates, you start your first image on the local solar noon at that date. The analemma will be just in the center. Or you can choose any date you like, but you must use the local solar noon time of these dates. And here is an image just to explain. I'm not sure if you can see my mouse. Here is the 4 dates, 1, 2, and 3, and 4, and they are in the center. So on these dates, on their local time, if you're looking south, they will be exactly on south. So next, the solar analemma chart and what is it for? The solar analemma chart is just the solar analemma overlaid on a scaled chart in degrees, vertical and horizontal. Sometimes horizontal is by minutes. So
Can I just say there that your presentation isn't updating, so you need to find a way of showing the images that you're talking about, if that's okay.
Okay. Which image are you on right now?
I'm looking at the very first image that you have up. It seems to have frozen the screen right now.
Oh, okay. Okay, so I'm doing it this way. Can you see now?
Yes, that's better. We're seeing number 3 now.
Okay, so
that's number 1.
Yeah. Now I'm back to number 3.
Yes.
Yes. So yeah. So the vertical axis, this line in blue, represents the declination angle of the sun. And the brown or the horizontal axis represents where would be the sun on every day you're taking this picture. So sometimes it will be to the right of the frame, sometimes it's going to be to the left of the frame. And it's measured in degrees, and degrees can be translated into minutes by just multiplying by 4. So what's the use of the analemma, or some of the usages? For example, and this is to make it simple, let's suppose that you are on the equator, and it's the 15th of September. So you look at 15th of September here on the declination axis. It says here 3. So the declination angle is 3, and you can conclude the sun elevation angle on that day by subtracting 3 from 90. I don't want to take long time on this, so I'll just move to the next one, and if anyone has questions, I can go in more details. So the first thing the solar analemma is good for is determining the sun declination angle on any date. Second, determining the local solar noon time on any date. And finally, using this information with conjunction with the solar noon time at Greenwich or at London to determine your latitude line. And I've seen a presentation on your channel maybe a few days ago. Someone was explaining this, so I will not take more time explaining it. For the factors that govern the solar analemma, we know this is the shape of the solar analemma on the right. So we have this solar analemma if there is no axial tilt in the middle, or the one on the right here is the solar analemma if there was no orbit eccentricity. So we have orbit eccentricity as a factor and axial tilt. They both work horizontally, and of course the declination angle is vertically. Next to that is how these factors that I mentioned and show diagrams for how they produce this unique shape of the analemma. But before I start, I should make a reminder of the sidereal day and the solar day, because they will be very important next. A sidereal day is the Earth rotating 360 degrees, and that's not exactly 24 hours. That's 23 hours and 56 minutes. Basically, moving from position 1 to position 2, that's a sidereal day. If you are in any location, you would see the same star in the same location after 23 hours and 56 minutes. That's a sidereal day. But by that time, you moved in relation to the sun around a circle. So you covered roughly 1 degree when you come to this point. So you'll have to pass on another 4 minutes or 1 degree in order to be facing the sun and accomplish a solar day. So the first factor we're going to talk about is the sun declination angle, and here we have the Earth without the tilt. We give the tilt to the sun or the ecliptic plane. This is the equator and this is the sun angle. So the declination angle is the angle between the sun and the plane of the equator. And here is another image just to make it more clear. If this is the Earth with its tilt, then this would be the subsolar path or the ecliptic plane. Basically, this is the path where the sun is perpendicular to along the whole year. So, for example, on the equinox, 23rd of September, the subsolar point would be here, and after 1 month, it would be here on a different latitude line. Next to that is the factor of orbit eccentricity. So before I start, I should make note that this the circle that you see is an ellipse, 583 pixels by 584, and its eccentricity is 0.058, and that's a lot elliptical more than the Earth orbit. So when I show something like this, you know it's not reality, but just to explain. So we'll start in position 1. Let's say that you are in London and you're 12 noon. You're facing the sun, and say after 20 days later, you're not facing the same direction in space. You're facing like 20 degrees left of your original place, because we know that every solar day has an extra degree of Earth rotation. So you're pointing to this point in the space, but because the Earth was so close to the sun, it was speeding up, and the change in the relative position of the sun was so rapid, and the Earth rotation couldn't keep up with it. But moving from position 2 to position 3, when the Earth slows down, now the relative position change of the sun is not as rapid, and they catch up together. And then when it slows more, between 3 and 4, then the opposite thing happened. And basically, if I look to this and start saying that this is position 1, then after in position 2, the sun would be to the left. In position 3, the sun would be centered again. In position 4, the sun would be to the right of the observer. So that's how the orbit eccentricity affects the solar analemma. And now we move to the axial tilt, and for that I have to presume a perfect circular orbit, and to start with no axial tilt. Explaining this, what we see is these red and blue disks are the subsolar path and the equator. I'm basically interested in the outer rim of these 2 disks. So, and this brown here, let's say it's a starting point, where you see this yellow bar represents the direction to the sun on that day, And this green patch here represents a specific longitude line. So after a few days, they should move with the same speed in a circular orbit and no axial tilt. They both covered the same amount of angle on the same plane, so they are matching up on each other. But now let's give it a tilt. When we give it a tilt and look from top view, this is what happened. We're looking perpendicular on the plane of the equator, or the plane of the equator, and you can see that there's observable shift here when you look from a different angle. I'm just showing you the angle here, and I'll make exaggeration of the tilt just to make it more clear. So at this starting point here, it should be the equinox, where the two planes intersect with each other. So this angle on the red plane, or the red plane, is the same angle of the green on the blue plane, but because they are tilted, you see now the green is ahead of the yellow one, and they match up again on 90. And then the opposite happened. The yellow, or the sun, speeds up more than the longitude line that we took, and then they meet again on the next equinox, and so again. They're just like this. Finally, number 6, a glance at the math and trigonometry needed to plot the solar analemma. And I will not go through equations. I'll just show the trigonometry, the concepts of trigonometry. So the first thing, we need to know how far the subsolar point traveled. Like in this diagram, we know how much angle it covered from a certain date or certain time. So we'll take that starting point as the equinox, and from there, as the Earth moves, we can measure the angle of the subsolar point, how much it covered since the equinox. But the Earth movement is not fixed speed. It works with orbital mechanics, so we need to know where's the perigee, or the closest point when the Earth is at closest point to the Sun. That's on 3rd of January. We use this only to predict the position of the Earth on any given day, and using that we can get how much the subsolar point covered, how much of angle it covered. So this calculating how far the subsolar point traveled from a reference point along the plane of ecliptic. So we get this angle here from orbital mechanics, the angle covered by Earth in its orbit, with the equinox being reference point. So we have this angle. This is what we concluded, and then we presume any radius, any just arbitrary value, say 1, to start making triangles and solve these triangles in different projections. So if this the hypothesis, we have the hypothesis, we have this angle, and we have this is the right angle. So now we have the y and the x. The y and the x are on the plane, on the red plane of the ecliptic. So next. So this is the x when I was looking perpendicular on the ecliptic, but I want to know x on the equatorial plane. So I have this x, and I have the axial tilt, and this is the right angle here, so I can conclude the x after the tilt. This might sound a little bit vague, but if you look to the next picture, you'll understand what I mean. So compare this picture, y and x with tilt, with this picture here. Sorry. Yeah. So now that I know this x, I can conclude this angle, which is basically how much it covered in relation to this longitude line that I've been tracking. And I'll play a video. I hope it works. uh, just to show this 3D shape. Ranti, if the video is not showing, I hope you can tell me.
I'm just waiting for it to come through now.
It starts by a black screen, but then it should start playing. It's playing now. Is it showing?
Okay, I'm not actually getting that.
Yes, okay, so there's a problem maybe with this. Well, in the video, I was just showing this this drawing moving in 3D. So this, as I showed, is the projected X, and I know this angle between the red plane and the projected X is the axial tilt of the Earth. So now I have the hypotenuse, the projected X, I can get the Z. And since I have the Z, I also have the R, this yellow bar, so I can get this orange bar. So I solved all these three triangles, and I know their angles now. So the angle between the green and orange, this green and orange, is how much the sun is shifted to the left on that longitude line on the specific day for taking the solar analemma. Because on the first day it was in the center, the sun was in the center of the frame pointing south. But after a few days, now the sun is still to the east to him. And also in the first frame, when they was here in the equinox, the sun angle, the sun elevation was or sun declination was 0. But now after that certain time here, the sun became higher, and it will continue to get higher when you go to this end. But until here, the angle, the declination angle of the sun, as I showed in the first pictures, is between the yellow and the orange bar, and we can conclude it. So I forgot to say in the beginning that my background or my scientific background is just high school. So I dig my way through these things. I'm not that good at math, or I don't know much about astronomy, and maybe some of the audience here may object on the terms that I'm using, that they're not perfect, or not the official terms of things. But the point is, I struggled through this, and I put the equations together on a spreadsheet, and it produced the solar analemma. And like for example, this one here, I just remove the axial tilt from this one, and so it comes like this. Remove the eccentricity from this one, it comes like this. So all these diagrams are from my spreadsheet. It's not something that I downloaded. And when I compare this analemma with any analemma that exists online, any image, it matches perfectly. And it helped in my sun calculator to predict the solar noon for any location. I just put the coordinates, I put the dates, and it gives me the solar noon and any other information like time and date or suncalc.org. So with this, my finding and my experience, that's why I cannot think that the Earth is flat. And that's the end. Thank you.
Okay, thank you very much. Right, we're going to take a little break now. If you just want to pop yourself back on just want to pop yourself back on mute again, and yeah, that's great. I'll play a bit of music, and then we'll have you back for some questions.
Yeah, give me 5 minutes. I'll send you a message when I'm here. Okay.
lights are almost in the clouds, and their feet are chained to the ground with their chains of misery. They've got a hold of me, they won't let go of me. Let go of me. They might have gravity on their side, but something's pulling us high. Got the potential to fly. Don't let them be what holds you back from this one incredible chance. They're lucky to have had a glance at you. Are you defy gravity? They can be cruel and mean and a huge pain. Our heads are in the clouds now. Don't let them make it rain. A smile can be the sign they're missing out on their rainy day. They might have gravity on their side, but something's pulling us high. Got the potential to fly. Don't let them be what holds you back from this one incredible chance. They're lucky to have had a glance at you. Are you defy gravity? You defy gravity. They say we aren't strong enough, we don't have what it takes. I say yeah, they're wrong enough, and we'll show them someday. They might have gravity on their side, but something's pulling us high. Got the potential to fly. Oh yeah, don't let them be what holds you back from this one incredible chance. They're lucky to have had a glance at you. Are you defy gravity? You defy gravity. You defy gravity. Yeah, yeah. At you, are you defy gravity?
So, Crowxe, are you still there, my friend? Hello? Do I need to give you a call? 1 second, guys. I might have to bring him back.
Hello?
Hello.
Can you hear me?
We can, yes. Glad to have you back.
Yeah.
How's
Yeah,
it
thank
going? No problem.
Yeah.
So, okay, so we've seen the presentation. So, we've seen the slides that you've put up. We do have a few questions already. We have a question from Jason McCormack. Now, he's actually a concave earther. So, the question is, could it happen on a concave earth as well?
sure. The concave Earth is the opposite of the ball Earth. So some things might work, but I'm not sure if this is one of them or not.
Okay, we have a question from Mr. Tim Osman, who asks, how do we know the sun isn't just a hologram or an aberration trying to make us think we are on a sphere by all measure and observation?
Well, from general experience, whatever that emits light and heat is something that we can walk to, even if we cannot hold it, like a campfire. You cannot hold a campfire, but you know where it is. You can cover a certain distance, and when you walk around it, it changes the relative position of, or parallax. It changes angle. So I don't think at all that the sun is anything but something that we can determine its location in 3D.
Okay, so we have, we have another question from Aaron Moorfield, who asks, ask if he gets the same Analemma looking north from the southern region.
It will be reversed. It will be upside down.
Okay, just waiting for a few more questions coming in, but I know that you're friends with Thrive and Survive, is that right?
Yeah.
And I believe you've debated him before on this question, on this topic?
No, at that point I didn't know anything about the solar analemma, but I said that he was the one that motivated me, because he mentioned the analemma. I said, what is the analemma? And he described it to me. I think he was in the Navy, so he knows these things. And when I looked into it, it looked too hard. I even launched a challenge for me and for everyone else on my YouTube channel, and since that day I started working on it until I solved it.
Okay, we have a question from Ali B. Well, it's more of a statement. Perhaps you want to refute this. He says that the sun does not emit heat.
Well, I don't know. I don't know what to say. Just feels hot when I look towards the sun.
Okay. Adam Meakin says that he's done this for a flat Earth also, and the effect is the same.
Well, I would like to see his spreadsheet, because I'm going to show my spreadsheet right now. I'm ready for the next question. I'm just opening it. It takes time.
Sure, yeah. We're just waiting. If you want to open that, if you want to present your screen,
yeah,
I'll pop you on.
Okay. Present where? Yeah. Okay. Can you see it?
Yeah, it's just coming through now. If you click off my, there you go, minimize that or something. There we go. Right. So do you want to tell the audience what all this is?
So you see this thing with the green bar and the green column and pink and these colors?
Can, yeah.
Yeah, okay. So these are 365 rows of equations. I didn't, of course, write them all. I just wrote the first one, or the first line. I wrote it cell by cell in order for at the end to get this chart here. And if I zoom here, you see the two components, angle in relation, this component, sun angle in relation to empty focus. This is my own words. It means nothing except to me, but I understand what I'm talking about. It's this is the angle or the analemma, a result of the orbit eccentricity. So as you see here, it is like 0.07, 0.02 minus 0.01 minus 0.04 and so on. So if I made the first one to equal 0, right, and then I say to the next cell to equal the cell above, so now it equals also 0, and now I repeat the whole column. I repeat this to the whole column. So this the Analemma shape without, if we are orbiting the sun in a perfect circle. So I took in account everything, and when I check I mean, this is something that I plotted. So until I see that flat or concave Earth with this accuracy, I don't know.
Okay, so we have a question from LBB Store who asks, since we all view the sky with our eyeballs, is optical convergence of the viewer factored into these observations or ignored? Example, lights appearing to get lower in a hallway.
No, this Analemma is not just about our eyes, because you can have a tube, just a small tube, pointing it to the sun, and you take your image every 24 hours, and it will draw this shape. So it has nothing to do with our eyes. Actually, we cannot see the Analemma with our eyes because it's just overlaying picture over picture. So, yeah.
Okay, the Adam Meakin says that he was able to do the flat Earth, same as what you've presented here, by opposing the zodiacal rotation against the sun's rotation. Remember that the Analemma has been around since before the concept of the ball.
The Analemma, yes. I don't know the history of the Analemma, to be honest. It could have been back from the time of Adam and Eve, as observed, something that is observed. But we're talking about the explanation. And believe me, I've done a lot of search on YouTube looking for this Analemma, and the surprise is I didn't see even the globe side explanation like this one that I showed. So they talk about it in short, but there's no thoroughly explanation like this.
So in your opinion, this data that you have is what, conclusive?
Conclusive until I see equivalent data, not just because I've seen on the concave, I've seen the flat Earth Analemma. It just, talking concepts and theory, but it's not implemented to show the plotting, the actual plotting of the Analemma.
So what's your conclusion with everything that you've presented here with this data that you've got up on screen right now? Let me just pop you back on so that people can see this.
What?
What's your conclusion? You've got all this data inputted here.
Yes, my conclusion is that the three information of the heliocentric model, which is the orbit eccentricity, axial tilt, and the ball Earth rotation, they all work together, and when I do the math, they match my observation. So it's the heliocentric model is real. It could be a geocentric model, for example. This doesn't disprove the geocentric model. Just talking about the relationship between the Earth and the Sun. Which one is orbiting the other? This presentation doesn't say.
Okay, I'm just going to wait for a few more questions to come in. If anybody's got anything, we'll give you probably 45 seconds to say something. If nobody comes back with anything else to ask you, we'll round up the stream. It's as simple as that.
Yeah, okay, well, I have something
here we go.
to say.
We have a follow-up question here, so... Right, just bear with me. I am referring to the perceived angular distance of the Sun to the ground. How much of the perceived angular distance is due to optics of the viewer, and how much is rising curve? Now that's from LBB Store again.
Well, yeah, well, I did answer, I'll give the same answer. If you hold a tube, with a lens on it to burn a paper, all right? And every day, every 24 hours, you point that tube towards the sun. You point the end of the tube while the start of the tube is held on like a hinge, right? So after a whole year, that lens will burn the shape of the analemma on a paper. It has nothing to do with our vision.
Okay, can I ask you all? You know, you've done all this. This is a personal question for myself, but have you tried mapping this on a flat plane or a concave plane? Because there is some people in the chat saying that this might have, you know, what they observe may well be able to be applied in a concave as well.
I'm not sure about the concave, and I couldn't. I would have loved to try this, but for example, the movement of the sun on a flat Earth between the Tropic of Cancer and the Tropic of Capricorn, how fast does it move? I mean, is it just like a ping pong ball? It goes to the Capricorn and reflects and change speed directly and go back to the Cancer? I don't know that, so I couldn't build any equation. I even thought of it as a pendulum. You know, I thought of that the flat Earth is rotating under the sun, and the sun is moving towards the north and towards the south in a pendulum motion. And when I tried to inspect that pendulum motion, it didn't match reality, so I couldn't plot it.
Okay, let's just see if we get any more questions in. You was making a statement before. Is there something you wanted to clarify?
No, I just something came to my mind now. I thought I'd like to share it. I call it the Godzilla explanation or the Hulk explanation. It's, you know, we all know that gamma radiation changed the DNA of creatures. So is this a proof that there is Godzilla roaming somewhere and Hulk? So that's what I mean, because some people say the sun is moving according to electromagnetic fields. It changed the direction of light. So yeah, maybe the electromagnetic fields bend light in a certain way. But how can we know that this gives the effect? So until someone put the equations together and plot something that matches reality, or just like QEC says, it's independent variable and dependent variable. So my dependent variable here was the elevation and the azimuth of the sun, and my independent variable was locations or dates.
Okay, we have a question from Dysfunctional Navigator who asks, ask him if you would do this at solar noon, would it be a straight line?
Come again?
If you were to do this at solar noon, would it be a straight line?
Oh, I think I got his question, but I'm not sure he's asking it the right way. The analemma would look as a straight line. I don't know. I'm not sure, but I know that if there was no axial tilt and the orbit was complete circle, the analemma would be a dot in the middle of this chart.
Okay, we have a question from Hazmat who asks, why does maths and models make truth?
Well, math and not math and models. It's math and trigonometry, or in fact, it's trigonometry. Yeah, I wanted to talk about this. Like for example, relativity, quantum mechanics. It's all equations and a little, very tiny bit of trigonometry. So I get lost in this math. There is no way to confirm it. But what I showed here is more trigonometry, and it's like a lazy person sitting looking at a building with a certain dimension, and he wants to paint that building. So there's two ways. The first way is to measure the area of each side of the building physically, go there and measure it. Or while sitting in his place, he determined the altitude and the width and the depth of the building, and then he does some equations and he get the total area of the building. And when he buys the paint that covers that area, and he painted perfectly, no waste of paint, no shortage of paint. That means his math or trigonometry was correct and it matches reality. So all these equations is just my tool, because I cannot physically go to the sun. Or also, there's a way to do it physically. I'm sorry. Yeah, if you build a small scale heliocentric model, and I'm talking like you build it in a room, you can get to this conclusion also, but it needs to be worked out with high accuracy. I don't have this accuracy. I don't have that kind of tools. I mean, if someone with a brain and brain more than mine, because I'm very bad in making models. With maybe $500, he can recreate the heliocentric model, and will come to these conclusions.
Okay, so Hazmat has a follow-up question, which is, how do you know that you are right?
Because I compared the Analemma that I plotted with the Analemma that I found online. And for example, I talked about the 15th of September in my presentation, and said that the declination angle would be 3 in the 15th of September. So if London is on 51 latitude, right? Randy?
Yes. What's that? I'm sorry. Sorry, it's your presentation. I'm not
Okay.
To help you out here.
Yeah. So London is on latitude 51. So if you subtract 51 minus 3, that's 48. Subtract that 48 from 90, you get a 42. If you look the time and date on London, 15th of September, you will find it around 42 degrees. The elevation angle at solar noon, it will be 4 degrees.
Okay, so Dysfunctional Navigator follows up with this question about if you did it at noon, it will be a straight line. You can do it for yourself. The Adam Meekin puts, does your guest realise that this is observational data, that the heliocentric model is backworked to fit?
This is what?
It's backworked to fit.
No, you can say backward, but you can say like reverse engineered.
Yes.
To get the design. Yeah, I can say so. Just reverse engineered and I get rid of the result. So if you can see my screen here, I put the 15th of September in the input date here, this one on the right. And the solar noon for that date is 1140, and the sun elevation on zenith or at solar noon is 42 degrees, same as I concluded by the Analemma. In fact, this is derived from the Analemma.
Okay, so the Rumpus asks, you only needed eccentricity and axial tilt to give the movement of the sun we observe in real life, and that a flat earth model would not agree with reality, question mark.
Okay, yes. It will not work, for example, because the elevation angle of the sun on a flat earth model is never less than 15 degrees. But I know this model is not accepted by many flat earthers.
Okay, so just to clarify though, that you have only ever tried to map this out on a globe rather than do it on concave or a flat?
Yes, and as I said, I didn't have enough information to do it on a concave or flat. And as I said, for flat, it uh, it wouldn't work because the sun, the minimum elevation angle of the sun on any place on Earth would be at least 15 degrees.
Okay, I'm just seeing if there's any more questions come through.
Yes, okay.
Okay, so a dysfunctional navigator again has come back about his noon question. He's clarifying it now by saying it is about solar noon versus local noon.
Solar noon, oh no, I call it local solar noon. And if he's talking about navigation, then the local solar noon, the solar noon at certain point with the clock of London, that makes me find which longitude line I am on. I guess that was what he means. That's 101 navigation. Or if you want to clarify the question again, I'm ready.
I can ask you a follow-up question again from LBB Store, who says, is sun elevation in your math referring to how high from the ground the observer perceives the sun to be? Would this not include the optical convergence of the viewer?
Okay, the angle of the sun measured, or the angles measured in the elevation angles, they are measured from the plane of the equator. A pure geometrical derivation, just something that is at a certain height in relation to this plan and a certain distance. I don't know the distance, and I don't know the height, but I know they're relative to each other. So it just derived pure geometrically, and it matches when we take time lapse along the whole year, and it would match again if you just use any mechanical tool to track the sun.
Okay, well, I think that's all the questions we're getting so far. I'm just going to see if anything else pops through right now.
Okay.
So, Dysfunctional Navigator again is asking, is your local noontime the same as solar noontime on the clock that you use?
Local solar noon is the same as what?
As the solar noontime that you use on your clock.
Well, we don't use the local solar noon for plotting the analemma or taking an image of the analemma. We don't use the individual daily solar noon or local solar noon. We just start at a certain solar noon, local solar noon time, and every day, every 24 hours, 24 hours is the mean solar day, because the solar day itself, it grows longer and shorter, but the main solar day is 24 hours. So I start by a certain local solar time, and that time I add 24 hours every day, and taken the next image.
We have quite an interesting question here from Chris Cruel, who asks, do you think if you made any assumptions in your presentation, does it invalidate any observations or data that you've obtained?
I would say yes, but there's no assumption. Okay, just to clear things, there's three numbers that I used in this presentation. I had no mean or no way to know that the Earth eccentricity is 0.0167. I don't know that. The Earth tilt, I don't know it. The Earth rotation, I can conclude it, yes. But the other two information, this is what we've been told. This what others made some reverse engineering and said that this is the model. And what I did is I put the model to test. This is just my demonstration. I put it to test. Someone tells me specific details. When I put them together, they match the reality or the truth. The reality, not the truth.
Okay, so still waiting for any more questions to pop through. I'll give it another 30 seconds. If I don't see anything in the next 30 seconds, then we'll wrap up.
Yeah, there's a question that I've been expecting, but I didn't hear it yet.
Do you want to sort of ask it yourself?
Yeah, is this the trigonometry you used? Is that Euclidean or non-Euclidean trigonometry? I don't know. It just works.
Yeah, you asked you in your first email to me. You actually mentioned that.
Yeah.
Okay, right. If you want to pop yourself back on mute, I'll just do a little bit of a chat, and then I'll give you the floor for 5 minutes to round up. So I'm just going to tell a few people about what's happening this week.
Yeah.
So, right, this week it looks like we are getting Right the Hand to come in on Wednesday and do a presentation, which should be pretty awesome. On Friday we have a gentleman called Jeffrey. I'm not going to give his full name because obviously I don't want to dox him in any way in case he doesn't want to give his full name, but Jeffrey will be doing a presentation at 6 p.m. and hopefully, and I'm pretty sure that Adam's already got this all worked out, Adam Meakin will be doing a presentation at 9 p.m. this coming Friday as well. So next week it looks like we're going to be having Bob the Science Guy. He looks like he's going to be getting a presentation ready to do. And I'm in the discussions with a few other different people for next week too. So this week already we've got 3 different presentations from people that you might not have seen presentations from before. 2 of them will be flat earthers, 1 of them will be a glober. And yeah, I'm looking forward to it. It's all different topics as well. So that's the plan for this week. If you want to take yourself back off mute now, Crow, and yeah, I'll give you the floor for 5 minutes. If there's anything you want to say, promote your channel, promote other people's channels, whichever you want to do, the floor is yours.
All right, thank you. Well, I'd like to give a shout out to some channels, if that's okay. So, and I will start with Flat Earth channels. Dr. Zach, or Decimal Z, Steve Torrance, Mr. Thrive and Survive, David Marsh, of course Flat Earth Brothers for his decency. All of these channels, I learned some things from it, and they motivated me to do some things. And for the globe side, I can say my role model is Flat Earth Math and Wolfie. In fact, Wolfie, with his equatorial mount, this was the spark that started me tracking the sun and end up building the sun calculator and the Analemma grapher. I have playlists in my channel. I'm interested in the challenges that I've made, and they are tough challenges, really. I would like if anyone take a look at them. And well, that's all I think. Thank you all.
Can you tell everybody what your channel name is? Can you spell it out for them so that they can go and find you?
Yes, it is Crowxe.
So is that all one word?
Yeah, that's all one word. Crowxe.
So it's CROWXE, and you are available to find on YouTube right now. And you say you've got some challenges there for people to do. Is that right?
Yeah.
Okay, fair enough.
Okay.
Fair enough. Right. If you want to pop yourself on mute again, my friend,
Yes, okay.
that would be great. Okay, well, guys, thanks very much for stopping by. I hope you all enjoyed that. If you're a glober, you've probably seen that presentation a few times. If you're a flat earther, you've probably never seen that presentation before. As has been said before, the gentleman had only ever mapped it out on a globe, had never tried to do it on a concave or a flat. So who's to say whether that data itself would actually work on those models too? But it was an interesting chat. Thank him for stopping by, and I hope everybody decides to tune in on Wednesday when we've got Right at the Hand at 6 p.m. BST. Be there, and I will see you all in the next one.